hi everybody. Today we're going to prove three main theorems of cardinality. The first of these theorems is the following, even though it's very surprising, is that the rationals have the exact same size or cardinality as the natural numbers. So the theorem is that the size of Q is the same as the natural numbers. Okay? So to start, we first let Q plus be the set of all positive rationals. Now, as a set, Q plus looks like this. The idea is to list all the elements in Q. Remember, to be countable, it means you can just list the elements in that set. So, first we're going to list the elements in Q plus, then using that list, we're going to list the entire rational numbers. So first of all, define for each n in the natural numbers the following set. Now I'll explain this set in more detail in a second. So A subscript n is the set of positive rationals where the numerator plus the denominator equals the subscript you've picked. Okay? So as an example, A1 would be empty. Why? Because remember, the natural numbers start at 1. If you add any two naturals, the smallest number you can get is 2. So there is no fraction when you add their numerator to the denominator that you would get 1. So A1 is just the empty set. On the other hand, A2 has one element in it. Then basically the fraction 1 over 1. Why? Notice these are both natural numbers, and 1 plus 1 is 2. A3 has two elements in it, 1 over 2 and 2 over 1. A4 has three elements in it, 1 over 3, 2 over 2, 3 over 1. You should try the rest of these, but you just keep going. So for each n, you get these. By the way, it's a good induction proof for yourself, or a good proof, to show that in general, an has n minus 1 elements in it. Just as a note, for those who are interested, the size of an is going to be n minus 1. But, like I said, just you pick the subscript, now you look at all the fractions whose numerator plus the denominator is equal to n. Okay, so we have this list, A1, A2, and A3, and A4. Now do the following. Look at this list that you have, A1, A2, A3, A4, A5, and so on. Now, A1 has no elements, so you don't need to pick anything from that. But basically what we're going to do is list Q plus. Now, A1 has no elements, so there's nothing to do. We look at A2, well, we put A2 has 1 over 1 in it. Perfect. We put it here. Then A3 has 1 over 2 and 2 over 1. We put it there. I'm just going to show you how this is picked in a second. A3 has 1 over 3. Now notice it also has 2 over 2, but 2 over 2 is the same as 1 over 1. So if the rational number you get is not new, that is, it's already occurred in the preceding to it, then you just cross it out and you don't put it in. So this 2 over 2, while this is one of the things, you don't pick it. Then you have 3 over 1. A5, if we put A5 here, let me just Make this a little. Well, A5 is 1 over 4, that's perfectly good. Then you have 2 over 3, that's also good. 3 over 2, that's also good. Then you have 4 over 1. So none of these have repeated before, so you keep them all. On the other hand, if you come to A6 now, well, it's 1 over 5 is new, but 2 over 4 is not new. 2 over 4 is the same as a half. So you don't put this in your list. Then you have 3 over 3. Well, this is not new. 4 over 2, this is not new. 5 over 1 is new. So you keep these. And you continue. So the idea is, you call this number, because it's new, you call this A subscript 1, small a, by the way. These are sets, these are elements. You call this A2. You call this A3. You call this A4. You call this A5. A subscript 6. Small a, by the way, again. And what you've just done is constructed a list of the positive rational numbers. Every positive rational number occurs in this list. Why? If you pick any rational number, it's of the form P over Q. So you should note, for any x in Q plus, x is of the form a over b, where a comma b are natural numbers. So x is an element of this set. Remember, a subscript a plus b, remember by definition, this contains the fractions whose numerator is a and denominator is b, or of that form, that they sum up to a plus b. So over here, every positive rational numbers occurs in this list. And because we've eliminated the things prior, if it's repeating, it occurs exactly once. Okay, so one thing that you should realize is that a set is called countable if, by the way, a set, I'll say A, is called countable if the cardinality of A equals to the cardinality of the natural numbers. Otherwise, so a set, an infinite set, that is not countable is called uncountable. As we saw in the previous theorem, a set being countable is the same as saying you can list its elements in a sequence without any repetition. The idea is the following. If A is countable, then there is a bijection F from the naturals to A. And what does that mean? It means you have F of 1, F of 2, F of 3, F of 4, F of 5, and so on. And each one of these is an element in A. And because F is a bijection, more specifically it's a surjection, every element will occur in here, and because it's an injection, every element occurs exactly once. Hence the idea of a list. So basically being countable is equivalent to saying you can list the elements. That's why the previous proof, all we did was list the elements in Q. And that was sufficient to show that Q was countable. Okay? Our next theorem is a very famous theorem that says that R is uncountable. Now, this is a very famous theorem, and the proof, it uses a notion called, or a proof called Cantor's diagonalization argument. Now, first of all, so what we're going to show is that the elements in R cannot be listed, like we listed them in for Q. Now remember, the cardinality of R is the same as the cardinality of the open interval 0, 1. So we will show that the cardinality of 0, 1 is not equal to the cardinality of the naturals. And because these two cardinalities are the same, this means the cardinality of the naturals is not the same as the cardinality of R, and hence R is uncountable. Now, how do we do the proof? Most times, not always, but most of the proofs about showing something is uncountable is you assume it's proof by contradiction. So you assume it is, and try to show you get a contradiction somewhere. So assume that 0, 1 is countable. Remember, we're going to prove this notion, and because these two sets have the same size, if we can prove this, we've proven that R is uncountable. So if 0, 1 is countable, then there exists a bijection F from the naturals to the open interval 0, 1. Now we can list these elements. You can think of them as f of 1, f of 2, f of 3, f of 4. I need to erase the bottom portion. F of 5, and so on. And the idea is, all of these are decimals, so they look like something like this. Where you can think of these as their digits in their decimal expansion. Okay? So now, the idea is, if this is a bijection, every element in 0, 1 has to occur exactly once. Okay? So, and they have to occur. But we're going to show that we miss an element in 0, 1. In other words, this map we've constructed, which we assumed was a bijection, it actually isn't a bijection because it's not surjective. Now, remember, we don't know what F looks like, but we have to show that the image of F will miss a point in 0, at least one point in 0, 1. So we're going to construct an element. Construct the following element. So A is going to look like 0.A1, where these are the digits of A in the decimal expansion. And I'll give an example shortly, where the kth digit of A, so remember this is AK, you can pick any number you like, any digit you like between 1 to 9, whatever one you like. Well, I've picked 5 here. So pick AK to be 5 if the kth digit of f of k is 4. So when you go to f of k, so for example, for A2, if I go to f of 2 and I look at the second digit of f of 2, if the second digit happens to be 4, I pick A2 to be 5. And pick it to be 4 if the kth digit of f of k is not 4. Okay? Now, to see how this works, I'm going to give a concrete example. So normally in a normal class setting, I would let you pick the digits, but suppose for the sake of argument that you have this. Now the idea is that this thing is never going to be in the image of f. Now, just for a concrete example, suppose, let me just pick a different color. Suppose this one was 4, 3, 1, 2, 3, and so on. Suppose this was 4, 4, 4, 4, 5, and so on. Then 2, 5, 9, 3, 1, so on. 3, 3, 3, 3, 3, and so on. 5, 5, 5, 5, 4, and so on. Suppose these were the first few in your list, okay? The idea is, for A1, so before I write this down, you should try writing it for yourself, but let's figure out what A would look like for this example, okay? At least the first few digits, this would give us the first few. Now notice, this says, look, so for A1, I have to look at the first digit of f of k. Well, the first digit of f of k is 4. This says if your first digit is 4, A1 is going to be 5. So I put a 5 here. For A2, I look at the second digit of f of 2. If it's 4, I change it to a 5. For f of 3, I look at the third digit. So I am looking at these digits for each AK. And if I see a 4, I change it to a 5. If I don't see a 4, I change it to a 4. So this is 9, so this becomes a third digit is 4. This is 3, so this becomes 4. And this is 4, this becomes 5. And we continue as we go down the list. And if you notice, A is not equal to f of 1. Why? Well, they differ at the first digit. I changed the first digit. A is not equal to f of 2. Why? Because when I constructed A, I made sure it differed from f of 2 at the second digit. Same with f of 3. I made sure they differ at the third digit, and so on. In particular, if A was equal to f of k, then the kth digit of A would equal the kth digit of f of k. But this is impossible. After all, I made sure they didn't equal to each other. In other words, A is not equal to f of k. For any k in the natural numbers. And this says that f is not surjective. So a contradiction. Okay. Now, a couple of remarks. First, is there anything special about 5 and 4 that we picked? And the answer is no. You could basically pick any two distinct digits. I could have picked 5 here, 7 here. I could have picked 1 and 9. The idea is you just have to make sure you're switching the digits. Okay? All right. And you should try constructing this for yourself, but also convince yourself that this proof actually shows that the cardinality of the natural numbers is in fact not the same as any set with the set with binary sequences. So, for example, if I have a sequence of zeros and ones, infinite sequence, that set is uncountable. If I have an infinite sequence of zeros and ones. Because really what this is is constructing an infinite sequence of 5s and 4s. And what you're showing is that such a sequence is uncountable. Okay, the second comment that I have, and it's a question that maybe you have asked yourself already, is why do we pick the diagonal entries? The question is, could you pick, say, the first entries? And the answer is no, you can't just pick the first entries. Try this and you see something goes wrong. So for example, if I said A1 is change the first entry of F1, A2 change the first entry of F2, A3 change the first entry of F3, that method will not work. Think about why. And maybe a third result, the diagonal is very easy to remember, but the construction can be different. This would have worked if I said, pick the first entry of F1, pick the third entry of F2, pick the second entry of F3, pick the fifth entry of F4, pick the fourth entry of F5. In other words, if I told you to pick distinct entries in each of the things listed here, again it would work. The reason we pick the diagonal is because it's very easy to see where we're picking which elements to pick. But as long as you're picking a different digit from each of these ones in your list, you're going to get a construction of an element that doesn't appear in the list, contradicting the fact that your function is surjective. Okay. I know sometimes this is hard because most people have questions during this time, but you can always ask them in our online sessions or the discussion board or Piazza. Okay? So the third of these theorems that we're going to prove today revolves around the notion of what is known as the power set. So first of all, here's a definition. For any set X, the power set of X which is denoted by P of X, is the set of all subsets of X. Okay? In other words, what this means is that A is an element of the power set of X if and only if A is a subset of X. So there's a very nice relationship between elements of the power set and subsets of X. They coincide with each other. As an example, okay, if A is the empty set, think about what would the power set of A be? Sorry, if X is the empty set. Think about what the power set of X would be. Before maybe you look at this answer, maybe you could pause the video here for yourself and see if you can answer this. But the power set of X becomes, so while X itself is empty, the power set has one element, the empty set. Why? Because the empty set is a subset of every set, namely is a subset of itself. If X is a set with one element, again, you might want to pause the video here. What would the power set of X be? Well, it would be the empty set and X itself. If X has two elements in it, then the power set of X would have the empty set, the set with a single element A, the set with a single element B, and X itself. So a couple of things, and you can continue this way. One, if the size of X is n, remember we already proved a while ago that a finite set with size n has how many subsets? If you look at your previous proofs, we showed that it has 2 to the n distinct subsets. So then, the size of the power set of X is 2 to the n. The other remark that we can have is that for any set x, the empty set is always an element of the power set of x, and x is always an element of the power set of x. Why? The empty set is a subset of x, and x itself is a subset of itself. Okay. All right. So now we are going to prove one of the more famous theorems by Cantor, and it's the following. The cardinality of x is not equal to the cardinality of the power set. Just as a, by the way, just as a side note, in fact, the size of x is always less than the size of the power set of x. This second fact, this fact here tells you that there is no set with largest size. Okay? But what we're going to prove is this major theorem, main theorem, is that the size of x is not equal to the size of the power set. Assume it was. Assume the size of x equals to the size of the power set of x. Okay? Then there exists a bijection f from x to the power set. Okay. Now, first of all, we have to understand what this function tells you. So maybe picture-wise this is easier to see. If this is x and you pick a point A here, okay, then f of A is a subset of x. Why? Because f of A is an element of the power set. And by definition, being an element of the power set means you're a subset of the set x. In other words, f of A is something like this, picture-wise. By the way, this picture is deceiving because f of A could contain A, or it could not. So it could either be like this, or it could be something like this. This is your x again, this is your A, and f of A could be this set. But it could be one of the two. You don't know. But this is the thing that Cantor's genius took advantage of. Okay? So, over here, he observed that when you look at this f of A, it's possible for this A you've picked to be an f of A, or it could not be. Okay? And he uses this in the proof. So I need to erase some stuff. So he constructs a set. So define D to be A and X such that A is not an element of f of A. Okay. So remember, like I said in this picture, every time you pick an input, f of that input, so if your input is A, f of A is a subset of X. Then either your input is an element of that f of that input, or it's not. And the construction of D here is the set of all x such that the input doesn't end up in the subset constructed by the image of f under that input, or evaluated at that input, sorry, that was incorrect. So A is not an element of f of A, okay? So for example, just as a side note, if in your example x was z, okay, and f was going from z to the power set of z, and so remember now, f of 1 would be a subset of the power set. And suppose for the sake of argument, you picked 1, 3, and 4. which is a subset of Z, then 1 is an element of f of 1. So, by this construction, 1 is not in D. Because here it says D consists of all elements of X such that this doesn't end up in f of A, doesn't end up in f of A. On the other hand, if f of 2 is 1, 5, and 7, for example, then 2 is not in f of 2, so 2 would be in D. Okay? And so on. So this is a set. Now notice, where does D sit in? Well, D, by definition, elements of D come from X. So D is a subset of X, which tells you D is an element of the power set of X. Now remember, F goes from X to the power set is a bijection. Okay? In particular, it's surjective, which means what? It means if I pick any element in the power set of X, I have to be able to find an input that goes to that element. Well, D is an element in here. So since F is surjective, I'm going to use a different color because I feel like this marker is losing its juice. Since F is surjective, there exists a Y in the set X such that f of y equals D. So this is in here, D is in here, there must be an input in here going to D under F. I'm calling this input Y. Okay? So remember, Y sits in X. Okay? Now, f of y is a subset of X, namely this D. So, there are two options. Either y is an element of f of y, or y is not an element of f of y. Okay? So remember, f of y is a subset of here. Either this picture happens, or the other picture happens where y sits in f of y as an element. But one of the two has to happen. So, or the one that looks like this. One of these two scenarios has to happen. Now, if y is in f of y, then y is not an element of D. Why? Because by definition, you're in D if you're not an element of, if A is not an element of f of A. But this would say, but D is f of y. So this says y is not in f of y. The contradiction. On the other hand, if y is not in f of y, by definition of D, y would be in D. But then this says y is in f of y. Again, a contradiction. In other words, we know one of the two cases has to happen, but they're both giving us a contradiction. And what does that mean? This means no such f exists. In other words, there is no bijection between X and the power set of X, and hence the cardinalities are different. Now, this is quite amazing because of the fact that for any set you pick, the power sets will never have the same size. In other words, consider Z. So this says Z, the power set of Z, the power set of power set of Z, the power set of power set of power set of Z, and so on. These all have, so no two sets here have the same cardinality. Okay. Well, I hope this helped, and I wish you luck during the term. Stay safe, and take care of yourselves.